Alright, here we're back again. Now we're going to reflect on a few things. Starting off, we talked about just last time at the end, a mirror, as a light ray comes in, it's called the incident ray. It bounces off, and that's called the reflected ray. If we were to draw a line parallel to the surface of the mirror, that's called the normal. The normal means perpendicular to. Remember the normal force back in the day, where the force is perpendicular to the surface. Alright, well, this is the normal. And the in between the incident ray and the normal is the angle of incidence, and over here between the reflected ray and the normal is the angle of reflection. And these angles will always be the same as it reflects off. Alright? Now, when we see something that's been reflected, alright, we are actually seeing what we would call a virtual image. Okay, now kind of used to virtual reality. You're seeing something that's not really there. Well, that's kind of the same thing in a mirror. Alright, if you have a mirror, say you have a candle in front of it, the light hits there, bounces off, and so it appears to be coming, but for someone who's looking at over here, it would appear as if the mirror is coming from behind the mirror. There's a candle behind the mirror. Same thing would be here, just someone brushing their hair. Alright. You see the second part? Let's move that over here. Alright, so you can still see it. Okay, and so if she's brushing it, it looks as though she's back behind the mirror. And a lot of people use this to advantage, and put in restaurants will put like especially if they're small, they will put a wall of mirrors, and it adds a lot of depth. It looks like there's a whole other room on the other side, and so it makes the room feel much larger than it would be if you just had a wall right there. But this is a virtual image. If you're looking at the candle, there's actually light from the candle coming up to your eye. But here, the image in the mirror, if she looks at the image in the mirror, it looks as though the light is coming from behind the mirror and the actual image is back there, but there's not really an image back there behind the camera. It's an illusion. And so that is a virtual image. Alright. Now, for example, if you saw a movie on the screen, that is considered a real image because the light is coming from the screen where it appears to be. Okay? Even though there's not actually, say, a car going over a cliff or whatever's happening on the movie, the image is considered real because the light that you're seeing is coming from the screen, and that's where it looks like it is. Whereas with a mirror, it appears to be back behind it, and that appears to be where the light's coming from, and there's really no image there. And so that's the difference between virtual versus real. Now, some other differences. Notice that if she has, it looks like a hair straightener there or something, or a curling iron, I'm not sure exactly. But you notice that it's on her right side, and yet on the person in the mirror, if you were that person, it would be on their left side. And so the right and left, side to side axes have been flip-flopped. Okay, if you were to reach out with your right hand, instead of the image reaching out with their right hand, as if you're going to shake hands, you just end up touching your right hand, what would look like to their left hand. And so that's been switched. The up and down is still the same, but it's not. Now, that is why you may see this sign on a vehicle behind you. Okay, but if you saw this in your mirror, top and bottom would be right, but it would be flipped over. And when it's flipped over, it would read ambulance. Okay, and so they look like they're written backward. But if you look on the front of ambulances stuff, they will have these kind of signs on them, so that when you see it in your mirror, it will spell ambulance, even though it's written backwards. Now it'll look fine when you see it in your mirror, and you'll know what that vehicle is and why they're getting up close behind you, right? All right. So let's look at one special example. Most of the time, we're talking about flat images. Like so, with a flat image, your image looks pretty much the same, other than the right and left sides are flip-flopped. Okay, but there are curved mirrors, which are used very commonly for various things. Okay, and one is a concave mirror. This one here would be concave. Excuse me, this one would be convex. This one here would be concave. Convex on this side, and concave on this side. Now, when you look at this one, the way the light reflects back to his eye, it looks as though it's coming from inside the mirror, and at the angle it reflects, it makes the image, the virtual image, look small. These are the type of mirrors you would use on your passenger side view mirror, and they have a little sign on the bottom: objects may be closer than they appear. Okay, made famous in Jurassic Park, among other places. But that's so that you can see a wider area on that side, and hopefully don't get blindsided by something. But it does make objects look smaller and therefore look farther away than they actually are. Okay, these are also used in convenience stores a lot of times up in the corner, and it allows the even though it kind of distorts things and makes things smaller, it allows the store clerk to look up and see a wide angle and a lot of the aisles and stuff for shoplifters and things like that that he needs to check out for. So those are some examples of what those are used for. Now on the other hand, the concave mirror, because it's like a cave, it goes inward in the middle. When it reflects, the way they reflect, it's at a much steeper angle, and so it makes it look like, if you're up close to it, then it looks like you'd be a very large image. Okay, and if you take a makeup mirror, a lot of times you'll see little mirrors on a stand. That's what these are. They are curved in, so if you get up close, it makes your face look horrible, to be honest with you, because you can see every little pore, every little pockmark, whatever, and sells lots of makeup, I'm sure, because people see it that close and it scares them to death, so they think, oh, I need to cover all this up. But that's just my personal opinion. But at any rate, it shows it up really up close and personal because, once again, it's a virtual image, but because the angle's different, it looks like it's coming from a much larger object in the mirror than it is. Now, just for the record, if you were to scoot this guy back farther, this ray would cross and come down, and this one would cross and go up. And if you're far away from a makeup mirror, things look upside down, okay, because of that. But if you're up close, and we'll talk about within the focal distance, but at any rate, if you have it up close, it will show things very, very large and magnify them. Now, the same thing would be done with the spoon, except for it kind of distorts the image a little bit, but you can do the same thing. Convex would be the back side of the spoon, and concave would be the inside of the spoon, and you can see these characteristics of those mirrors in that case. So here we are again talking about reflection. Let me see. This example is a picture of a virtual image. All right, he appears to be floating in midair because the science teacher, because his legs appear to be off the ground. And someone says, how is he doing that? But if you look closely, you'll notice there is a mirror that he's sitting on. And basically, you're seeing part of his leg here, and then you're seeing the reflection of this leg, a virtual image. So it appears that you're seeing a leg on the other side of a glass, but actually you're not. You're just seeing a virtual image of this leg reflected back on the other side. Okay, but it makes him appear to be flying, and mirrors are very important for a lot of optical illusions. Magicians often use them and things like that. All right, but getting on, how does this happen? Well, and why do some things reflect and some things don't? Basically, what we're going to talk about. And we have specular versus diffused reflection. Okay, specular is when we said if you look at any surface close enough, there's no such thing as a smooth, perfectly smooth surface. Some are smoother than others, but there's still, if you look at it microscopically, it can be rough. Okay, and in order for a reflection to be good, or what we call a polished reflection or specular reflection, this would be specular or polished surface. It can't have any irregularities or roughness, any bumps and stuff like that on paper. Have to be less than 1/8 the length of the electromagnetic wave that's being reflected off of it. Okay, if it's less than 1/8 of the wavelength, then it will be polished to that kind of wavelength. Now, this is a radio wave dish that's used, basically a radio telescope that's picking up radio signals from outer space. As you can see, it's not solid. It has all these little gaps in it, but radio waves are very long. We said some of them are up to football field in length, certainly meters in length. All right, and so even though there's holes in it, this acts just like a concave would, and like a concave mirror would focus light on one point. Well, this will focus all those radio waves and bounce them off right there to that center point, and they will not go through because, as far as it's concerned, the holes are so small compared to the wavelength of a radio wave that it bounces and it catches all those radio waves and focuses them on this point here. Okay, and so that's because radio waves have very large waves. Now, if something has a short wavelength, then it takes much less bumps to cause it to have what we call diffused. Okay, and diffused is basically, let's look at the drawing first here, I guess. If it's a rough surface, rather than having a nice equal law of reflection where the angle of incident and the angle of reflection are equal, they just kind of bounce off in all different directions. So you don't get even though it may reflect light, for example, a white piece of paper reflects light because that's what makes it look white to us, but it doesn't, you can't see your image in it because all the different reflections are going in all these different directions, and they don't make a cohesive image like it would off of a glass mirror. All right, and so it says, but paper is relatively smooth. If you feel it, it feels very smooth. But if you were to magnify it, you can see all the fibers in it here, and it is rough. And so it's not nearly as rough as these big holes in this thing, but that's because these are big radio waves that have 1 meter, 2 meters, or more wavelength. This is light. Light has extremely small wavelength, so even these small little irregularities in the surface are enough to mess up and give it a diffused reflection where it doesn't reflect a good image. Glass, on the other hand, is extremely smooth, and so it does, and glass mirrors are much better. Originally, people used metal mirrors, and then finally they figured out how to put mercury or silver on the back of glass and cause it to reflect better, and so glass is the mirror of choice ever since. Without the backing on a mirror, just a plain piece of glass, like in a window, will usually reflect about 4% of the light back. And so a lot of times you can kind of see your reflection in just a piece of glass mirror. But if it has something dark behind it, for example, your cell phone, when it has a black image, can be used as a better mirror. Or if it's dark behind it, then you can see your reflection better. All right. Silver, on the other hand, reflects about 90%. And so they say you polish the silver to and see your face shine in it. Well, basically that's what you're doing. You're getting to where you can see a good reflection. Now, the next thing we're going to talk about is refraction. Refraction is similar to reflection. Both have re in it, right? But it has more to do with how light is bent rather than just bouncing off or reflecting. Okay? And an example would be if you had two wheels, and you were rolling them, and they're on the sidewalk, which is fairly smooth, and they hit the grass. Well, since it's coming in at an angle, then, well, let's do this. Let's just say it came in straight, first of all. If it came straight into the grass, when it hit here, the two wheels would hit the grass, and what would they do? Well, they would slow down, correct? And so it would slow down, but they would both slow down the same amount because they're hitting grass. And then they'll get the other side of the grass, they would speed back up again because they're off the grass under a smoother surface again. All right, but if they come at an angle, this wheel hits first, and therefore it starts going slower, which allows this one to swing around a little bit. And so it changes the angle and pulls it toward the slower wheel. Kind of like if you're going down the road and you drop a wheel off the side of the road where it's rougher, it's going to pull your vehicle that direction, and you're going to curve your path toward the edge of the road. And if you're careful, you overcorrect and you go spinning around the road, but that's a whole different thing. But it's the same thing. If it slows down one of the wheels, it's going to pull it over. Well, the same thing is true of light rays. As they come into something that slows them down, water, glass, all these things we talked about earlier that slow down the speed of light, okay, then they are going to slow down. And if they come at an angle, the part entering first will slow down, and that will cause the whole wave to bend. So instead of coming here, now it kind of bends off and goes this direction. In this case, instead of going, oops, sorry, my drawing not too good, instead of going straight out here, it bent more closer to that perpendicular line, or the normal. Right, it bent it toward the normal. Water is a good example of that happening. If you look at water, although we'll talk about lenses also, but if you have an angle of incidence coming in toward the water, when it hits the water, this bottom part is going to slow down, the other side is going to speed up, and it's going to bend it toward the normal. Okay, and so your angle of refraction, since it's not being reflected, refraction, notice, is not the same as your angle of incidence. Okay, you've changed those. Whereas with reflection, angle of reflection and angle of incidence are always the same. But when it's been bent, coming in at an angle into water, which slows it down, it will turn, just like the wheel over here did on the grass. Okay, this is important. For example, if you were a bow fisherman or something like that, and you were trying to shoot a fish in water, okay, it bends, and so if you shoot where you appear to see the fish up here, because when it comes to your eyes, here's the light coming from the water, it bends toward your eyes, so it appears to be out here somewhere, but you have to shoot kind of behind that if you want to actually hit the fish, because the way the light has been bent, and that can cause you to miss them a lot of times. If you try to grab something underwater, the same thing would happen. Okay, and so